Okay, so the session is now being recorded, so that's good. Tonight I'm going to make a few opening remarks as I usually do, and after I make some opening remarks, then I will give Linda an opportunity to say anything she might want to say, and then certainly students can chime in anytime, as Linda can chime in anytime, but I will give you specific times to do it, and then we're going to do some content. We're going to talk about chapter 23 tonight, and so that's kind of the program, and so on and so forth. And Linda, I do realize that you have another commitment, so you're going to be leaving in the very last few minutes. But until then, I hope you're feeling up to doing maybe some calculator kind of things for us as we go forward.
Of course.
Excellent. Okay. All right. So there are 3 more meetings counting tonight, which means there's 2 meetings after tonight. Tonight we're going to talk about Snell's law and some other things in chapter 23, and that more or less finishes the things that I think we have to cover. There's much more that I could teach you about physics and things like that, and I may have some of those things that I'll do on during the next 2 periods. But one thing that's going to happen on the period of on next Wednesday is I will make everybody aware of, okay, what's on the test, topically wise, what do you need to prepare for, and things like that. And then we will have our VCM test on the in class on the Monday of final week, and it'll begin at 6 o'clock and end at 7:50. Everyone should make note, in case that causes your arrangements to be different, that we do go till 7:50, so I'm giving you some additional time for that. This is the time where you don't want to be letting up, though. You want to be finishing strong. There have been some people, and I think they know who I'm talking about, who I've been seeing working really hard in the Learning Commons, and that's good. And that I think will pay them some good dividends, and it will pay you all good dividends to be preparing. And maybe I'm going to turn it over now to Linda to see if she has anything she wants to add or report. So Linda, the floor is yours.
Yeah, so the traffic at the GSGs is still a little slow, but I did actually have some people come into the Learning Commons to chat with me as well. So just so you guys remember, my hours are about 9 to 3 on Mondays and Wednesdays. You can find me on campus. Tuesdays, I'm in there from about 9 to 2, and then again from 3 to 6. And then on Thursdays, then it's roughly 9 to 2. So any of those days, you guys can find me in the Learning Commons. Just say that you're looking for me.
And and I realize that people have constraints and things like that, so everybody can't do this. But face-to-face is so much better, I think, than remote. Okay, now I'm going to throw it open for any student Q&A and things like that before we jump into things. Okay, seems like there's no questions, so let's just jump into some things. Now, the first thing I'm going to do, even though this has been covered in the lectures that I asked you to watch, just so we can have some decent discussion here, I am going to point to a couple of things from the end of the chapter review. Now, the end of the chapter review here is really talking about electricity and magnetism, and perhaps you should be thankful that you don't have to worry about electricity and magnetism, because electricity and magnetism interact in the way that's shown here, and these are basically sine curves, but they're perpendicular to each other, and it's pretty well, it's pretty complicated. Now, but one thing that is on this slide that I think is useful is that the intensity or the power is proportional to the square of the amplitude. And so What that is saying is, and this is a question that's on many certification exams, and that is that what is the energy or the intensity proportional to? And the answer is it's proportional to the amplitude squared. And so that's one takeaway from this this slide. This is talking about the nature of light, but actually what happens is if you drop a pebble in the water or if you have a point source, we actually, oh, there is a question here. Okay, hold on. I think what that question or comment was about is that I am not current with spaces for people to upload the LSAs. And so I will take that as some just criticism, and I will fix that. So thank you for the comment. And by the way, if I misunderstood the comment, you can ask it again. But I think that's certainly I want to do that because those things count for you. They count for you. They also help you understand the material, and so all that is good. Okay, but sound works the same way. So you have waves and you have rays that indicate the direction of sound. So a wavefront is a surface of constant phase wave moving with a speed equal to the propagation speed of the wave. So that means in the case of light, this is moving at the speed of light, but in the case of sound, this is moving at the speed of sound. And you know that the speed of sound depends on the medium that you're in. And so a ray is a line along the direction of propagation, but is perpendicular to wavefronts. And so what you can see is that all these angles are in fact 90 degrees that the purple lines are making to the blue lines. Now this is probably the heart of what we're going to be talking about tonight. This is a big thing. I am sure that on the final exam, there'll be some questions about this. And
You may need to
Linda,
reload the collaborate session. I can see it. I'm not sure if other people are having the same problem.
and at least some people are chiming in saying they can see it, I can see it, and Linda can see it. So I think that advice will be good to just, exit, collaborate, and re-enter, or whatever Linda said. I think that's more or less what she said. Okay, now this is, and you can make this bigger. So anyway, I'm going to talk a little bit about this, and we're going to be talking about reflection and refraction, and this is some of the boundary behavior that happens, and it works very much the same way for light as it does for sound. And so please, please keep that in mind. And I'm just going to be reading from the slide a little bit, and maybe I should get my pencil to use as a pointer a little bit. Okay, so things have things called an index of refraction, and that is a number that's called N. They're calling it N for index, and the index of refraction is equal to the speed of light in a vacuum divided by the velocity that light has in the substance. So you can see if the substance has a tendency to slow down the speed of light, then V is going to be a smaller number than C, and that means that C over V is going to be bigger than 1. So the index of refraction is telling us how thick, and thick is the wrong word, but how retardant the substance is to light, and how it slows it down. Okay, so that is one fact. And in fact, down here in this little picture that's at the bottom of this slide, you see that you do have a substance A that is shaded blue, and a substance B that is shaded. I'm going to call that a peach color. And so what you have is you have a boundary, and you have a boundary where substance A gives way to substance B. And so there is a boundary there, and so things happen out the boundary. So there are a number of things that are happening at the boundary, and if you look down here at this little picture, what you will see is that in this little picture, they're conveying that the index of refraction of substance A is less than the one of B. Now, what that means is that instead of, and look at what happens here, we have an angle of incidence and an angle of reflection. So this angle right here is the angle of incidence. So that's angle this is coming in, and that's the angle that we're striking this surface. Now, students should make note of the fact that this angle is drawn relative to, and the angles that we're going to be talking about for the most part are going to be drawn relative to this dotted line. And this dotted line is perpendicular to the surface. So that is a normal line. That's what people call it. And so the angles all are drawn relative to that. But so what we have is this rays coming in at an angle of theta sub A, and it hits the surface. Now, two things happen at the surface. One thing is that some of this is reflected, and it's reflected in, and you can see still the purple arrow. So it comes in, it hits that point, and it bounces back out. And this is one of your facts, and that's this facts up here. And that fact says that the angle of incidence equals the angle of reflection. And so that happens here, and that's a law of optics, that's a law of sound as well. But in addition to some of this being reflected, some of it is transmitted forward. And we have coefficients of impedance and things like that that I talked about in the video that determine how much of this energy actually is transmitted into the denser substance and how much of it is reflected. And we'll probably do some calculations with those along the way too, not so much tonight, but perhaps later. So one thing that we know is that the angle of incidence equals the angle of reflection. Okay, so that's one of the things that we really want to know. Okay, another thing is that there is a law of refraction, and it is found right here. And this is called Snell's law, Snell being a person's name, that is S-N-E-L-L. And Snell's law gives you this equation for what really is happening here. Now, Snell's law talks about the incident angle and the angle of refraction, which is called theta B in this picture. Okay, so here's what you have. You have a ray that is striking the boundary, and some of it is reflected off at an angle that's equal to the incident angle, but some of it also goes into this denser surface, but it is refracted. And when NA is less than NB, it's going to be moved closer to the normal. And the equation that governs this, that we're going to be using for calculations and things like that, is the one that's shown up here. And it says that, and I guess I will try to write it a little bit bigger. This says that NA times the sine of theta A. So you see down here, that means that we're in this region, and the angle to this normal to the surface is given by theta A. And so if I take the product of NA, which is here, times the sine of A, that is going to be equal to, and this is one manifestation of Ohm's law, is equal to NB. times the sine of theta b. And so, yes, you're going to be using your calculators, and that's one of the reasons I ask Linda to, please have her calculator nearby, because we might be doing some of those calculations tonight. Okay, so that is one version of Snell's law. There's another version of Snell's law that is important for ultrasound, and that has to do with the velocities of things. And we'll talk about what Snell's law says about the relative velocities. But you see, these things will move at different speeds. And so the signal is refracted at an angle, but also the speed can change as you go from one to the other. Okay, so that is what we have there. Now, when a ray travels, and this can happen in ultrasound as well as in electrical signals, when a ray travels within a material at a greater index of refraction towards an interface of one with a smaller index of refraction, total internal reflection occurs when the angle of incidence exceeds a critical angle. So we're calling this critical angle theta critical, and theta critical is the angle where the sine of theta critical is equal to NB over NA. And I remember, I don't know if Linda remembers it or not, but I remember when I was younger, I wrote a test where I gave them a Snell's law problem, but I just made up the numbers and things like that. And I had something that was exceeding the critical angle. And so I was dealing with a thing where there really was even no refraction, and I was asking them about that. So anyway, this is a calculation that you might see in some of the problems. Okay, so it's kind of complicated what's happening. You have an incoming ray that hits the boundary. Some of it is reflected and some of it is transmitted into the other surface. But what is transmitted in is bent, so the angle changes, and that means that the speed changes. So incident, reflected, and refracted rays and the normal all lie in the same plane. The angle of incidence equals the angle of reflection. And here you see that the sine of theta A over the sine of theta B is equal to NB over NA, where those are the index of refractions. So this, that's a lot of what we're going to be doing. So be prepared to, have us talk about this quite a bit as we go forward. And let's just weigh in and do a couple of problems, and some of these are going to be having you, let's see, I need to look at the next one. Yeah, so we're going to do a couple of these as sort of warm-ups, and this is a little bit of review, but I'm going to read this one, and then I'm going to ask Linda a question, as well as asking her to stand ready with her calculator. Okay, so I'm reading question, it's just called question 1 here. A solar flare erupts on the surface of the sun. So there's a flash. It almost looks like a volcano, or like somebody taking a big flash picture on the sun. How many minutes after it occurs does light show up in an astronomer's telescope on Earth? Okay, now Linda, and it does say consult Appendix E. We're not going to go looking at Appendix E, but I'm just going to ask Linda. Linda, what's something that you would like to know to answer this problem?
Well, you probably need to know the speed of light.
Yeah, so the speed of light is something that I'm going to tell you what it is right now. Now, we saw, because there were index of refraction, that light could travel at different speeds, but in a vacuum, which is what really happens between the Earth and the Sun, what happens is we know the speed of light. And that usually is being denoted by c, because Einstein called it c. And the speed of light in a vacuum is 3.00 times, and this is going to be 10 to the 8th, and that is meters per second. So Linda is always right, and she's right again this time. We certainly need to know the speed of light. But since they ask us about time, Linda is thinking that distance equals rate times time, or distance equals velocity times time, and they're asking how many minutes. Now you got to be a little bit careful in doing this problem, because you see I gave you the speed of light in meters per second. So there's no minutes down there. So this problem involves some dimensional analysis, which makes it a good thing to review. Okay, so how many minutes after does it occur? So anyway, and Linda knows that distance equals rate times time, or distance equals velocity times time. And I just told her velocity. So Linda, what else do you need to know in order to do this problem?
You would also need to know the distance between the Earth and the Sun.
Okay, and so that's another piece of information that you need to know. And maybe those will be in grace notes or something, but I'm going to give you that distance as well. Okay, and that is, and another word for this would be the orbital radius of the uh, Earth about the sun. And you see, if this were the sun, the Earth rotates around it, not exactly in a circle, but pretty more of a circle than what I drew there. But anyway, so the distance is going to be this distance right there, and that's called the orbital radius of the Earth, and that number is, and I will just call it r because I'm calling it radius, and that is equal to 1.50. It's really kind of convenient for the arithmetic with the with the significant digit part of this, and this is then times 10 to the 11th meters. Okay, so we got both of these things in meters, and we know distance equals rate times time. So I'm going to ask everybody to give this one a go, and tell me what you come up with. But be aware that the question that you were asked was having to do with minutes, not seconds. So everybody give it a go. Linda, let's give them about 2 minutes to do this, and then we'll go through it. And Linda, I'm watching the time, so I'm going to call that, but I may ask you for some calculator assistance on this problem. And Linda, I'm going to share my screen on the whiteboard. Oops. Okay. I think I hit the chat instead of the sharing of the screen. Sorry about that. So I'm going to share a whiteboard. Okay, so distance equals rate times time. That was one thing that we were talking about. So D equals rate times time. And this was, so that means that time is equal to distance over rate. Okay, and so distance over rate then is going to be the distance it goes is 1.50 times 10 to the 11th. And that is meters. And this is then divided by 3.00 times 10 to the 8th. And this is meters per second. This is meters per second. And so whenever I do that, I will get seconds in the numerator. And when Linda does this, Linda, I think I can almost do this myself. This is 500 seconds. Is that right?
500, yeah.
All right, but that's 500 seconds. So you have to turn this into minutes because the problem asks for minutes. So this is 500 seconds. And we're going to take this times, and we're going to have the seconds cancel. So we're going to have 1 minute per 60 seconds. The seconds will cancel. And Linda will divide that, and I think she will get, and she'll check me on this, but I think it's going to be 8.33, and I'm going to stop there, minutes.
Yep, you got it.
Okay, so what that means then is that the flare that you see on the sun, or that the person with their telescope saw on the sun, actually isn't happening when they're seeing it. It happened a little bit over 8 minutes from then. Now, so this was a little bit of dimensional analysis review and a little bit of equation review. Distance equals rate times time. Okay, so I'm going to pause for a count of 5 or something to see if there's any questions, but otherwise we're going to go and do another problem. Okay, so I'm clearing all of this, and I'm going to go back to, or in fact, Linda, maybe can you bring back the screen, or do I have to stop sharing, or? Yeah, there was a question that was asked about calculators in Excel. I'm certainly going to give you Excel, and I will give you access to the calculator on the screen calculator, because you're going to be taking this on your basically you're going to be doing this on your PC. I mean, this will be in Blackboard, and I'm going to give you a password. You're going to do it that way. So yes, you can use a calculator, but it's going to be the calculator that's on the computer screen that you have, and or you can use Excel. So I think that answered that question. All right. This is a little different problem. I'm going to read problem 3. I'm going to ask everybody to do this, and I guess there's really two things here. Someone is asking, can the calculator do degrees and radians? And it can do both. And I would encourage you not to go into the final exam. So I would play with the calculator before that time. But the answer is yes, it does trig functions, and it also does degrees, both in radians and in degrees. Angle measures there. Okay, so we're doing number 3. I will read it, and we'll talk about, there's a part A and a part B. Linda and I will give you 5 minutes to do this one, but it's a little bit different, but it also has some similarities. Okay, how much time does it take light? And again, Linda would probably say, oh, we need the speed of light, but I already told you the speed of light. It's down there. It's that 3.00 times 10 to the 8th meters per second. Okay, So that is good. So how much time does it take light to travel from the moon to Earth? And it tells you that the distance is 384,000 kilometers. Now, again, this is a similar problem, but you have to realize what's a kilometer and how does that figure into my problem. And part B says light from the star Sirius, which is, I could be wrong about this. I'm not teaching astronomy right now, but I think Sirius might be the closest star to our sun. But anyway, light from the star Sirius, and if you look in the right place of the sky, you can see light coming from Sirius, but you're not really seeing the light of Sirius. You're seeing the light that Sirius gave off 8.61 years ago. So that's how long it takes to reach the Earth. So then this question asks, what is the distance to Sirius in kilometers? So there's a lot of dimensional analysis that's going on into this problem. But everybody begin working this, please, and we'll come back in, I think I said, I'm going to say 5 minutes, maybe 4 or 5 minutes. I'll keep the time. But we'll come back very soon and we'll go through the solution to this. You have enough information in the problem and what's on the screen to do this. So everybody give it a go with your calculator. And the student, I'm not going to recognize you by name, even though I did see your name. When you ask about that calculator, that would be good time to start investigating that calculator now, if that's what you're interested in. Okay, so everybody's working. I'll call time in a little bit. Okay, let's talk through these. So I'm going to share a blank whiteboard. And Linda, if I forget any of these numbers, you can help me remember, but maybe I will remember them. Okay, now again, this is distance equals rate times time. And the first question that was asked was, how long does it take light from the moon? And that's really not light from the moon, it's light reflected off the moon, because the moon does not generate any light. So distance equals rate times time, and that means that time is equal to distance over rate. And they were saying we had this, so this was 3 times, and I know it's 3.00 times 10 to the 8th meters per second. So that's in the denominator, but in the numerator is the distance to the moon. And they said it was 384,000 kilometers. Now you see you got a little bit of a problem here because you want to have seconds in your answer, but those kilometers and the meters don't cancel out. So we need to fix this. We need to have our unit be meters. So this is, we're going to be multiplying this by, we want the kilometers to cancel. That's going to be in the denominator. And there is 1,000 meters in a kilometer. So this kilometer will cancel with that. This meter will cancel with that meter, and the seconds will come to the top, and so we will have seconds. Okay, so Linda, how many seconds does it take for light reflected off the moon to reach the Earth?
That would be 1.28 seconds.
Okay, and you see that's because the moon is much closer to us. So that was 1.28 seconds. That was good. And then we had the star, which was 8.61. And people call this light years because it took us 8.61 years, but light was doing the traveling. So you see, this is the distance. Okay, or actually this is the time, excuse me. So this is years, but we want to know the distance. So this is time. So distance equals rate times time. So we say distance is equal to, this is time here, times the rate. And we know the rate is the speed of light. So it is 3 times, and this is 10 to the 8th, and the units here matter. This is meters per second. Okay, and so it's okay to have the answer in meters, but you see seconds doesn't cancel here. So what we have to do is we have to change years into seconds, and maybe we'll do this by steps. So I'm going to multiply this, and I'm going to change it from years to days. Okay, and so that means I'm going to be multiplying by 365.24 to count for leap years, 25 to count for leap years. This is days per year. And so what happens is the years will cancel with the years, but now I have days being multiplied by a speed that's given in seconds. And so I need to make this into seconds in order for the units to come out right. So I'm going to multiply this again by, I'm going to use a conversion factor. I want days to be in the bottom, but I'm going to use hours in the top. So this is 24 hours in one day. And so we have 24 hours in one day. And then I need to change it in seconds. Now I'm going to make a quantum leap here because there are 60 minutes in an hour and 60 seconds in a minute. And so that is 3,600 seconds. That's a 3600. And the unit is S divided by, and this is 1 hour because it's 60 times 60. So the hours will cancel, the days have canceled, and I have this in seconds. Okay, so you take this in seconds, and this seconds will cancel with this seconds, and Linda will pound that into a calculator and give us an answer, and she'll probably tell us not a whole bunch of zeros, but she'll probably tell us a power of 10.
So it's about 8.15 times 10 to the 16th power meters.
Okay, so that is a long way away from us. And if we put that in kilometers, which the problem asks us to do, we would have to change that to 8.15 times 10 to the 13th kilometers. Now I realize I put it in meters here, but the problem really asks for kilometers, and you should follow directions. Now, if you had the right number and the units were appropriate, that doesn't mean it's an F on the problem, but you do want to answer the problem the way it's asked. And so that would be the answer to the problem. Okay. Thank you, Linda. And we're going to erase all that, and we're going to move on. Now, I think I'm watching the clock, and we don't have too much longer before Linda has to leave. So I do want to get to our featured event. So Linda, let's go back to the PowerPoint show, and I'm going to try to look for some things that are dealing with. Now, it doesn't mean these other things are bad problems that you shouldn't do them. That just means we only have time to do so much here. And there's some very good problems that are there, but they're not dealing with Snell's law. And so we're going to find something that's dealing with Snell's law. Actually, there's a whole bunch of these. Maybe we'll come back and do some more of these whenever we come. And look, there's an intensity problem too. So you see, this is some really good review, but none of those were Snell's law. Okay, so we'll come to a problem here about Snell's law. And let's see, there's a couple of them. Okay, 34 is probably a good problem for us to talk about. So, a 1.55 meter tall fisherman stands at the edge of a lake, and he's being watched by a suspicious trout who is in the water. That is 3.5 meters from the fisherman in the horizontal direction and 45 centimeters below the surface of the water. At what angle from the vertical does the fish see the top of the fisherman's head? Okay, well, this makes us think, and this is not too different from one of the problems that I asked you guys to do as an LSA, but I'm going to go and start sharing my my screen with you. I'm going to try to draw this picture. Okay, so I'm going to share a blank whiteboard, and I'm not going to spend a lot of time drawing this fisherman. So here's the fisherman, and he is 1.55, and I think it said meters tall. So that's the fisherman standing there on the surface. And then there's a fish that's in the water, so he's at the edge of the water, but there's a fish underneath the water, and the fish is over here. I think this is 3.5 meters, which is a little better than 10 feet into the water. And the fish is, how deep is the water, Linda?
Let me open up that PowerPoint and look. I don't have it in front of me.
Okay. Okay, it may be 45 centimeters. Okay, that's what people think it is. Now, you really need to think about this because 45 centimeters. Okay, so we have that. Okay. And so what happens is that the fish, so this is where the fish is. Now we're going to deal with these units in a minute. That's my picture of a fish. But the fish is trying to look at the top of this guy's head. Okay, so the fish is and here I'm drawing a perpendicular to the surface. This is the surface of the water. Okay, so the fish is looking at this angle. So that's the ray that goes up. That's the line of sight of the fish. But the fish is in water, and water has a index of refraction of, I'll just call it water. And this is 1.33. Now, the index of refraction in air, where this guy is 1. So it's just like a vacuum. So N is equal to 1.00 up here. But then they're trying to get to the top of his head. Okay, so they're trying to look at the top of his head, but the point is that this ray is bent. So you see this theta that we're hitting the normal to the surface at here. This theta is not the same as this theta. Okay, and so what we really want to do is we really want to figure out what's happening here. And I think we said this was problem number 35, I think we said. Okay, so I'm going to give you guys, 5 minutes to work on this. And after you work on this for about 5, well, less than 5, let's say 4, because I want to be sensitive to Linda. And Linda's going to be pressing some calculator buttons kind of as she's grabbing her coat. I don't know, I think it might be cold outside, I'm not really sure. I don't pay much attention to that. Okay. Was there an angle in this problem too? Hold on. Linda, can you throw that problem up again, please?
Of course. Give me 1 second.
Apparently I didn't do a good job of reading the problem. I thought that was 35. Maybe that wasn't 35.
34.
No, 34. That's the problem. Okay, 34. All right, good. Okay, so I think I did do a good job of drawing that. Or let's go back to the whiteboard. I will share the whiteboard again. It says share blank whiteboard, but I think that will give me the whiteboard that I already had. But you see, this is the wrong angle here. I need to erase that one. So I'll grab my eraser and I'm erasing that angle because you see, that's not the angle with the perpendicular. The angle with the perpendicular is the other angle. And I warned you that students have trouble with that, and probably professors do too. So, and I know I called that theta, but that's not really theta because it's bent differently. Okay. And so what we're having, and I'm not even sure I like my picture so much here. I'm going to maybe redraw a little bit of my picture. Okay, so the guy's watching the fish, and this was 3.5, and now this is where the fish is deep, and so this is the picture that we want. So the fisherman is 3.5 3.5 meters from the edge of the water, and here's the edge of the water. And then we have the fish that is under the water. So the guy is here. The distance from him to the place where the fish is that 3.5 meters there. But then the fish is underneath this, and so the fish is underneath this at this is 45 centimeters. See, the problem's a little more complicated than what I was letting on, because the fish is over here at D. So here's the fish. This is a very bad picture, and it is not to scale at all. but here is the perpendicular that happens. So the fish is trying to look at the guy, and the fish is a distance d from this spot. Okay, so this is then the angle that we make with the, this is the fish's line of sight. So the fish is looking that way, and this is the angle that the fish's line of sight is making with the surface. But then what happens is it's bent to go to the top of the guy's head, and it is up here, and we know that this is 1.55, but we don't know anything else. But this is the angle that we get from, I will call it theta 1, that we get from Snell's law. Okay, so I need to kind of scamper here to take advantage of Linda's calculator prowess and things like that. So the d is the distance between this point and this point here, and where the fish is. And so what happens is that so the horizontal distance between the top of the guy's head and is going to be, so this is H, is the top of his head, and L is right here, is where you go into the water, and then this is where the fish is down here at point T. Okay, so the horizontal distance between H and L is going to be, so the horizontal distance between L and T, excuse me, between L, which is here, and T, which is here, is going to be, well, the T distance is going to be 3.5, and then it is going to be, so L and T is going to be, oh wait, this is the way the problem reads. So this is 3.5 minus D. I really messed up this picture. But anyway, I want to get to the Snell's law thing, and I've got 4 minutes to do it. Okay, so here's what this distance is, 3.5 minus D. This distance is D, and the whole distance that the fish was away was 3.5. So that's the way that hangs together. Okay, so here's what I can say. The tangent of theta 1, and this is theta 1 right here, is going to be, so the tangent of theta 1, we're going to do another problem after Linda leaves, but we're going to finish this one. This one was more involved. So the tangent of theta 1 is 3.5 minus D over 1.55. Okay, and the tangent of theta 2 is equal to D over, and this is 0.45, and we have that the sine of theta 1 times 1 is equal to, and this is 1.33 times the sine of theta 2. Okay, so we've got basically, we need to figure out, um, we have several equations and several unknowns. And this, I think, is going to go further than what Linda is going to be able to do calculators on us, because she's going to be leaving in about a second. And so I think what I'm going to do is stick a pin in this. We will return to this problem um, um, next Monday, or you could work on it in between. We're going to do an easier problem. And Linda, help me to remember to return to this problem whenever we meet again on Monday, and we'll finish this one.
All right, will do.
Okay, and 7 obviously does not like me punting like that, but I think it's best that I punt on this tonight. I should have managed our time a little better. Maybe not done as many problems as I did on that first part. Okay, so now I have the eraser, so I'll erase everything at once. We'll go find another problem. And Linda, do I have the, let's see, I guess I can just share my screen. It's not clear how I get, okay, so Linda's left the session. I hope you guys can still see me. And what I'm going to do is I'm going to share my application screen with you. And I'm going to throw up the PowerPoints that we were looking at. And wow, that means I have to go get them from Blackboard. Okay, so bear with me just for a minute. Okay, so I'm going to try to go and log into Blackboard. I'm sharing my screen with you, but I'm using a different browser, so that should still work. So I'm getting another browser, and I'm going to go to Blackboard, and I'm going to get those files from there. So this is, okay, so hopefully you guys can see me. I'm logging into Blackboard again. And let's see, this is going to be, and I will go here, and I will find our PowerPoint slides. I think they're in the syllabus tab. And I'll go all the way down to here, and this is December 1st. So I'm going to be sharing those. And so I'm opening that file now. And soon we'll finally be able to see the PowerPoint slides again. So I probably shouldn't have taken as complicated a problem as what I did, at least, and not allowed more time. This will eventually load up. Okay, so I'm going to enable editing, and I will just go through some I'm going to pick some of these that we'll go through and we'll talk about. And maybe it's easy, maybe we should talk about an easier problem first. Okay, so I'm going to make this a little bit bigger on your on my screen anyway. All right, so here's what we have. We have two plane mirrors. I'm talking about problem number 25 now. So two plane mirrors intersect at a right angle. And so that means that we have a right angle here, where the 11.5 centimeters and the 28 centimeters intersect each other. A laser beam strikes the first of these mirrors at a point that is 11.5 from their point of intersection as shown in the figure. For what angle of incidence at the first mirror will the will this ray strike the midpoint of the second mirror, which is 28 centimeters long, after reflecting from the first? Okay, so I'm going to stop sharing this, but I want us to remember 11.5 and 28 as the centimeters. And so we'll do this. Now this doesn't deal with Snell's law, but it does deal with the other law that I was talking about. Okay, so now I'm going to go back to here, and I'm going to be sharing again. So I'm going to share, and I'm going to be sharing my whiteboard. Okay, so here is what happened then in this story that we're studying. So you have a mirror that's here, and this is 11.5. And so we have a ray of light that strikes this. So the ray comes in like this and hits the mirror. Okay, but then over here, we have something that is 28 total centimeters. But we wanted to hit the midpoint, which means we're going to hit it at 14 centimeters. Okay, so what we're saying is, what angle do we have to hit this mirror at? And remember that the angles always happen this way. And the angles, and we're talking about the angle between the ray and the normal. So this is the angle that we're talking about, but the angle will go down like this, and I want to hit this at that point. So that means I have an angle here. I call this one theta. I'm going to call this one phi. This is a different angle. Okay. Now, what I can do is I can figure out what this angle phi is, and that almost tells me what angle I'm looking for. But I know that the angle of incidence, which is this angle, equals the angle of reflection, which is this angle. So that's the angle I need to find. But what we're going to be able to do, and I really should have done this problem would have fit in nicely. It's going to fit in nicely now. Okay, so this angle, theta, and the angle that I showed with two arcs like this have to be equal to one another. But I have this other angle that I have data on. So I know that this is 14 centimeters. This also was 11.5 centimeters. And the problem told me that these were at a right angle. So this is good because this helps us to review a little bit of trig. Okay, so and if we were in a classroom and I had a stronger relationship with you guys, I would I'll probably ask you guys questions about this. But the tangent of this angle phi is equal to, well, the tangent in a right triangle is the opposite over the adjacent. So that's a good review thing. So this is 14 over 11.5. Okay, and we can do that. Let's see. I'm sharing my screen. You're looking at a whiteboard. I'm going to ask someone to do this. Make sure that you're set on degrees. And Amber, I'm going to ask you. And Amber, if you're uncomfortable with this, I'm sorry. I'm not trying to make anybody uncomfortable. But what I'd like for you to do is make sure that the calculator that you're using is set on. Amber, you there?
Yeah, I'm here.
Okay, and if you're not, I mean, I'm not being mean with this. I'm just telling you. I'd have Linda do it if she was here, but she's not here. So this is 14 over 11.5. So are you comfortable, Amber? And it's okay to say no. Are you comfortable pounding this into a calculator?
Um, I don't remember how to do the negative tangent.
Okay, that's all right. That's fine. And that was an honest answer. And I'm not writing down, oh, Amber didn't know how to do this. That's not what we're about. Okay, so this is going to be the answer, but it's going to be the answer for this angle up here. So I'm going to go, and this will be a little bit of a good review, I suppose, because I'm going to share my screen with you again. Okay, so I'm stopping sharing the whiteboard. I'm going to share my application screen with you. And here is my application screen that I'm sharing with you. And now what you're going to see is this little calculator thing over here. And so I'm just going to type calculator. There's the calculator app. So I will click on that to bring it up. And soon we will see it. And I want a scientific calculator, and it gave me a scientific calculator. So that's good. And I have to think a little bit about this, but I think the way I'm going to want to do this problem is I'm going to calculate that first. So I'm going to say that was 14 divided by 11.5. I'm going to say equal. And so I get that number. But now I'm going to do the inverse tangent of this. Now I get the inverse tangent by hitting second. And then I look up here and you see I have to do second up here, excuse me. This is second and this is the inverse tangent up here. And so I'm going to say the inverse tangent of that. And the inverse tangent of that says that that was 50 degrees. In fact, it says it was close to 51 degrees. So I'm going to round that to 51 degrees. Now, so let's go back to the whiteboard. And there's the whiteboard that we have. So what it told me was that this was 51 degrees. And I'm just going to type that in here. This little angle right here, I'll type it again. This little angle right here is going to be 51 degrees. But you see, that doesn't answer the problem that was at hand, because the problem at hand was knowing what this angle was. So this angle that we really needed to know was 51 taken away from 90. And so this angle would be 49 degrees. Now, since the angle of incidence equals the angle of reflection, what I have is that the angle that we have to strike that first mirror at was 49 degrees. I actually like this problem. Okay, so let me talk about it again. So this was the setup. The angle of incidence has to equal the angle of reflection. So where I hit it, that's where I bounce off, and that's where I go. And I strike this other mirror 14 centimeters down. Now, using the tangent and the inverse tangent, I can figure out that this angle that I called phi is 51 degrees. That means the other angle has to be 49, and that means that the angle theta has to be 49. I'm going to pause for a count of 5 Mississippi, or maybe 10 Mississippi, to see if we have questions on this. 39 degrees. Thank you, Amber. Amber wasn't using, Amber probably did that without her calculator. That's horrible. You guys don't tell Linda that. How can I, let's see, what can I do? How come that's not erasing that? I'm going to try something else. No, you're correct. Okay, and I don't know why that's not erasing. So what I'm going to do is I'm just going to cross it out. Okay, and that should have been 39 degrees. And thank you, Amber, for paying attention and for doing the calculations along with me. Linda would have caught that. Actually, probably not much faster than you did, but that's good. So that is 39 degrees. And thank you, Amber. Okay, any other questions or comments on this problem? Yeah, the reason there was the 14 centimeters is because the words in the problem said you struck the second mirror at its midpoint. And originally the midpoint was 28 centimeters. So half of 28 is 14. I think that is answering your question. I hope so. Okay, good. And that just came from the problem. Okay, so we talked about the angle of incidence, angle of reflection. We still need to do a Snell's law problem, but we have the whole next period to do that. So I'm not worried about that. And if you want to work ahead, you can look at Snell's laws problems in the videos I posted and work on the one that I assigned. This was the guy who dropped his cell phone in the pool and he could just barely see his cell phone. Okay. All right, I do plan to have office hours again tonight at 9, and so you're always welcome there. And everyone be safe and good night. I will see you on Wednesday, and I'm going to have to turn the recording off because I want to post this.